Welcome to this series of videos on electricity and magnetism and modern physics. We'll start this by taking a look at a treatment of light, and we'll take a very quasi-historical approach. So to that end, over a period of a couple of centuries or so, there was debate within the scientific community over what the nature of light was. And historically, this could fall into two camps. One view was that light was some sort of a particle. People like Isaac Newton proposed that, or the fan of that, they explained a lot of things really well. For instance, how light bounces off of a mirror. It bounces off a mirror in pretty much the same kind of way that a billiard ball bounces off of a cushion in a billiard table. So that made a lot of sense. Other things, though, were a lot harder to do. You could do most of it, but it wasn't necessarily completely satisfactory. So there was another camp, and the person who is pushing this the most would be Christian Huygens, among others, that light was some sort of a wave. Now, we know that from our treatment of waves back in the series on mechanics, we saw that there are three major categories of waves. There's the mechanical waves, electromagnetic waves, and matter waves. Turns out light is an electromagnetic wave, but we'll have to go back and revisit this a bit. It turns out that the wave model explains a lot easier things like interference and diffraction, which we'll be getting into in the next few videos. But and you could certainly get the particle-like behaviors, but it seemed to be needlessly complicated. So there's a bit of toing and froing, but with time, and especially with Young's experiment, which we'll be getting to, eventually the consensus settled on the wave nature, until we get to modern physics. It turns out that there were a couple of small problems with the wave nature of light. And way into the future, when we, in this series of videos, when we get to it, we'll see that one of the problems was that it was predicted that if you shine light on to a metal, that you should eventually produce a current. Now, this is exactly how solar cells work, and we understand this now as photons of light coming in, liberating electrons out of the solar cell material and driving an electric current. Now, you can, with the wave model of light that we're developing, you can get that this current ought to happen. However, virtually every technical detail that you get differs wildly from experiment. And it turns out that pretty much the only way to save this was to revisit this wave-particle divide here. And we now say that's not either or, but it's both and. So everything has both a particle and a wave nature. Light and actually matter as well when we get to that point. This is at the core of modern physics, and the way that we will interpret this is that the wave property dictates the probability of detecting the particle. And this has survived all sorts of experimental tests, and it checks out really well. However, where we're going to be going with this for now is we're going to hold off on the modern physics approach, and we'll go with where we settled at just before issues with things like the photoelectric effect forced us to have a major rethink on the nature of light, and we'll work with the wave model. Much later, when we need to tie the two together, we will. But for now, just be aware that we're going to say that light is a wave, but in fact, we'll call it a transverse electromagnetic wave, and we will motivate what that looks like in the future. But there is also a particle nature to it, which we call a photon. And our modern understanding is that the electromagnetic wave nature dictates the probability of where we would see a photon should we go looking for one there. But for now, we'll stick with this wave nature here. All right. Now, as we work our way into this, I do need to introduce one idea. And I don't know really where else to put it, so I'm going to just start with it here. And this is a quantity called the index of refraction of a material. So the idea with index of refraction, it turns out it's really convenient for certain kinds of optics calculations. But what it really is it's characterizing the speed of light through a material. So the index of refraction, symbol n, is defined to be in the triple equal sign, means by definition in physics. It's defined to be the speed of light in a vacuum over whatever the speed of light is in the material. So the index of refraction is dimensionless, it means it has no units. And effectively, it's just saying how many times slower is light going through a material than through a vacuum. So the speed of light in a vacuum, that's always 3 times, just under, so I'll say approximately 3 times 10 to the 8 meters per second. And the speed of light in a material will always be less than the speed of light in a vacuum. So what this means is that the index of refraction of something will be always greater than or equal to 1. It'll be greater than 1. It'll be equal to 1 when it's a vacuum. And it'll be greater than 1 when light travels through anything else, because the material slows down the propagation of the wave. Now, it turns out that in the case of air, air is just barely bigger than 1. So much so that we will usually approximate the index of refraction of air as 1, but it is just slightly bigger than 1 in reality. This is something that matters, say, if you're an astronomer or in certain other applications, but for the rest of us, not so much. So just for a quick bit of review from thinking about mechanical waves, You'll remember that with mechanical waves, we looked at the scenario of what would happen if wave was, say, propagating down a string, and then suddenly it started propagating down a rope. And because the rope had a different linear mass density, the speed of the wave down the rope was different than down the string. So just real quick here, so this is going to be a bit of a pause and ponder moment here. If the speed of a wave changes, does the frequency of the wave change? The wavelength of the wave change? Both of them change, or neither of them change? Go ahead and pause the video for a moment and get back to me with your answer. Okay, so just by way of reminder, if the speed of a wave changed, the frequency of the wave stays unchanged. Yeah, we'll just say unchanged. And the wavelength is what changes. All right. So let's say we have a wave that was propagating in a vacuum. So in vacuum, we use the special symbol c for the speed of light in a vacuum. That would be equal to the frequency of the wave times the wavelength in a vacuum. By the same token, if the light is going through some material, we'll say that the speed of the wave through the material is v. It'll be equal to the same frequency of the wave. And this will be times the wavelength in the material. So I'll say lambda mat for wavelength in material. So now if I take this equation here divided by that equation there, so speed of light in a vacuum divided by speed of light in the material, that'd be equal to the frequency times the wavelength in a vacuum. This would be frequency times the wavelength in material. All right, so the frequencies cancel because, remember, at the speed of the wave changes, the frequency always stays the same. And this c over v, by definition, that is the index of refraction. So a little cross multiplication action here will give me that the speed, that the wavelength in some material would be the wavelength of that light in a vacuum divided by the index of refraction. And that's what's going to be useful here. And this is why people who work in optics usually think in terms of things like index of refraction rather than saying what the speed of light in the medium is, because usually you're just more concerned with how the wavelength changes. General rule of thumb, the denser the material, the higher the index of refraction, but that's not a hard and fast rule. So, for instance here, a typical wavelength for light, for visible light, is 500 nanometers. You'll be seeing the nano prefix a lot. That's a lowercase n there. And that means times 10 to the negative 9, so a billionth. So this is 5 times 10 to the negative 7 meters. So the wavelengths of light are very small. And that's kind of different from what we've seen with sound, where, you know, a typical sound wave that we can hear is roughly very roughly about the size of the speaker that makes it or something like that. And we know that speakers are kind of objects we can hold in our hands or at least in our fingers. And so the waves of sound are about that length. Light is very different this way. The wavelengths are a heck of a lot shorter. So let's go and take a look, say, at what would happen for, say, a typical value for index of refraction for glass. is 1.5-ish, and the exact value will depend very much on the different recipes for the glass. So if I wanted to get the wavelength of light in the glass, I would take that wavelength of light in the vacuum and divide it by the index of refraction. So that'd be 500 nanometers divided by, in this case, 1.5. So that's going to work out to be there we go, about 333 nanometers. So light traveling in glass will have a shorter wavelength just because it's traveling slower. It's going at 2/3 1/n. It's going at 2/3 the speed of light in a vacuum. So instead of 3 times 10 to the 8 meters per second, it's going at about 2 times 10 to the 8 meters per second in a typical piece of glass. Alrighty, so in the next video here, we will introduce Huygens' principle and then go ahead and take a look at Young's experiment. Catch you over there.